Imagine, imagine for a second that you're in charge of managing the traffic lights for a massive, sprawling city.
Oh boy, that sounds like a nightmare already.
Right. I mean, millions of cars, thousands of intersections, but every single time there's a traffic jam or, a detour or a parade,
Yeah.
you have to physically get in your car, drive to that specific intersection, open up this metal box on the corner, and manually type in commands to change the timing of that one specific light.
That is, it sounds completely exhausting. The margin for error there is just astronomical.
Exactly.
If you make a single typo while standing at that intersection, you could cause a massive pileup across the whole grid.
And yet that is exactly how computer networks have been built and managed for decades.
Yeah, it really is.
An engineer logging into one device at a time, typing commands, just, hoping they don't bring down the entire company.
Oh, the stress of hitting enter on a live router.
We've all been there. So if you're listening to this and you've ever worked in IT, you probably feel a knot forming in your stomach right now. But today, our mission in this deep dive is to explore a really fascinating stack of sources. We're pulling from Cisco certification guides, architectural blueprints, white papers on software-defined access, and we're going to demystify the absolute revolution of network automation.
Which is such a massive paradigm shift.
It is. We're charting this shift from that era of manual, error-prone typing to a world of software-defined magic, centralized controllers, and programmable APIs.
Yeah, for decades, network engineers relied on this totally distributed model. Every single router and switch was basically its own island, making its own localized decisions.
Right.
What our sources map out today is a fundamental redesign. We were literally separating the muscle of the network from the brain of the network to completely change how you operate infrastructure at scale.
Okay, let's unpack this. Because to really understand this new centralized command center, I feel like we first need to understand how those individual traffic lights, the traditional switches and routers, how they actually used to work on their own.
Sure.
The blueprints we reviewed, they split everything a traditional networking device does into 3 planes. But I'll admit, I'm a bit fuzzy on why we compartmentalize them this way. Why 3?
Well, we separate them because they require completely different types of computing power.
Oh.
So first you have the data plane, which is often called the forwarding plane. Think of this as the muscle.
The muscle, got it.
Yeah, its entire job is just processing and forwarding the actual data messages, so things like Ethernet frames or IP packets, and it has to do this incredibly fast. We are talking millions of frames per second.
Millions?
Right.
Wait, so it can't just rely on a standard computer processor, right?
Mm.
If it used a normal Intel CPU, the network would just grind to a halt.
Exactly. That's precisely why the data plane relies on specialized hardware. It uses things called ASICs.
ASICs. That's application-specific integrated circuits.
You got it. These are chips that are permanently hardwired for one specific purpose moving packets. That's all they do.
Wow.
And to look up where to send those packets instantly, it uses a special type of memory called TCM, ternary content addressable memory.
Okay, how is TCM different from, the RAM in my laptop?
So with normal memory, a computer runs a search loop to find data, right? It scans. With TCM, you feed it a value, like a destination MC address, and it returns the matching forwarding decision in a single hardware clock cycle.
A single cycle. That is insane.
It's blindingly fast.
So the data plane is all about raw, unthinking speed.
Yeah.
But the muscle doesn't know where to send anything without the control plane, right?
Exactly. The control plane is the brain inside the individual device. It runs the complex routing protocols.
Things like OSPF.
Yeah, OSPF to find the best path across the country, or spanning tree protocol to prevent local loops. The control plane figures out the topology of the network, builds the maps, and then it hands those maps down to the data plane's TCM to actually do the heavy lifting.
Oh, I see. So the brain makes the map, the muscle drives the car.
Perfect analogy. And then finally, sitting above both of those, you have the management plane.
Which would be the overhead tools for humans, like SSH, Telnet, things that allow an engineer to remotely log in and actually configure the device's settings.
Right, the interface for us.
But wait, let's go back to that control plane for a second. If every single router is using a protocol like OSPF to figure out the map of the network entirely by itself, that's like every single car on the highway calculating its own GPS route by only looking at the cars immediately next to it. They have no idea what the macro traffic grid looks like. Isn't that incredibly inefficient?
It is, and that specific inefficiency is exactly what birthed software-defined networking, or SDN. The big aha moment of SDN is realizing that we don't need 1,000 tiny, isolated brains calculating routes.
Right. That's just a waste of processing power.
Exactly. We take that control plane out of the individual devices and we centralize it into a software application called a controller.
So instead of those 1,000 tiny brains, you build one massive, omniscient command center.
Yes.
But how does this God brain actually communicate with the dumbed-down physical switches? Because now they don't have their own brains.
So in an SDN architecture, the controller sits right in the middle. It talks down to the physical networking devices, the raw muscle using what we call southbound interfaces, or SBIs.
Southbound, because it's going down to the hardware.
Exactly. And these can be modern protocols designed specifically for this, like OpenFlow or Cisco's OpFlex, or even legacy methods like command line scripts and SNMP. The controller uses these southbound interfaces to directly program those blazing fast data planes.
And then I'm assuming it has to talk up to the actual human engineers or the software programs that want to use the network.
Yep. And that happens through northbound interfaces, or NBIs.
So north is up to the software, south is down to the hardware.
You've got it. A software program doesn't need to know how to speak the complex proprietary language of a specific hardware switch. It just asks the controller for what it wants via the northbound interface, and the controller translates that intent down to the hardware.
That is so clean. But okay, if software applications are now sitting above the controller looking down at the network through that northbound interface, what language are they actually speaking to each other? Like, if I'm writing a script to automate my network, how do I place my order?
For modern network automation, applications and controllers communicate almost exclusively via REST-based APIs.
REST. That's representational state transfer, right?
Yes, and it's less of a rigid protocol and more of a strict architectural style.
I've always thought of a REST API like ordering at a restaurant.
Oh, that's a good one.
Yeah, like the menu is the API documentation. It tells you exactly what you're allowed to ask for. You can't just order a burger if they only sell pizza.
Right.
And then the REST API itself is the waiter. You give the waiter your specific order, the waiter takes it back to the kitchen, and the kitchen is the controller, which prepares the data and serves it back to you on a plate.
That is a fantastic way to visualize it. And the way you place that order with the waiter is by using standard HTTP verbs.
Like the ones we use for web browsing.
Exactly the same. The sources map these verbs to the standard CRUD actions of software development. Create, read, update, and delete.
Oh, okay. So how does that map out?
Well, if you want to create a new security policy on the network, you send an HTTP POST request.
POST, got it.
If you want to read a list of devices, you send a GET request. To update a setting, you use PAT-CH or PER2, and obviously to remove something, you send a delete request.
That makes so much sense. But the sources heavily emphasize that REST operates statelessly.
Yes, very important.
And I need you to break that down for me, because protocols like TCP, which basically run the whole internet, they're very stateful, they track sequence numbers, they remember the ongoing connection. Why does REST intentionally forget everything?
Statelessness is actually the secret to scaling automation. It means every single API request must contain all the information necessary for the server to understand and complete it.
So it's totally self-contained.
Entirely. The server, or the controller in our case, does not retain any memory of your previous requests. So if you ask for page 1 of a device list and then you want page 2, you can't just say, hey, give me the next page.
It means the waiter doesn't remember who you are.
Exactly. You have to explicitly ask, hi, I am this user, give me page 2.
I see. So the controller doesn't waste precious memory keeping thousands of individual user sessions open. It just answers the question and immediately moves on.
Yep. It frees up so many resources.
But what exactly is the kitchen serving back on that plate? Like, if I send an HTTP GT request to read a list of routers, it's not handing me back a stylized web page, right?
No, definitely not. And what's fascinating here is how the data is packaged or serialized for the journey. It's overwhelmingly served back as JSON, JavaScript object notation.
JSON, I see that everywhere.
Yeah, because JSON solves a massive communication barrier in modern IT. Think about it. Your network controller might be written in Java, but the automation script you wrote on your laptop is written in Python. Those two programming languages store internal variables in completely incompatible ways. They cannot talk to each other directly.
So JSON acts as the universal translator.
Exactly. It takes the complex internal memory of the Java application, flattens it out into standard structured text, sends it over the network, and then your Python script reads that text and rebuilds it into Python variables.
And it does this in a way that is incredibly lightweight, right? Because older formats like XML, XML was so clunky.
Oh, XML used those bulky HTML-style opening and closing tags for every single variable. Like if you were pulling data for 10,000 switch ports, all those redundant text tags would consume a massive amount of bandwidth and processing power.
Just a wall of brackets and slashes.
Yeah. JSON strips all that away. It relies on simple key value pairs. So like, in quotes, hostname, colon, and then router1. All organized cleanly with curly brackets and square brackets.
It's lean, it's fast, and honestly, if you format it right on your screen, you can actually read it with human eyes without getting a headache.
Which is a huge plus for troubleshooting.
Okay, let's pivot a bit. We understand controllers now. We understand the REST APIs and the JSON language used to command them. But how does this abstract software talk actually change the physical cables and switches in a building? Like, let's look at the Campus Revolution Cisco Software-Defined Access, or SDA.
Oh, SDA.
Yeah.
This is where we see the transition from abstract theory to a literal physical network revolution. SDA creates what the sources call a unified fabric.
A fabric.
Yeah, and to understand the fabric, you really have to split your mind into two layers, the underlay and the overlay.
Okay, let's start with the underlay. This is the physical realm, right? The switches, the routers, the fiber optic cables connecting the closet.
Exactly, the actual hardware.
The blueprints show that in a modern SDA design, the underlay uses a routed access layer, meaning every single switch, even the ones connecting directly to the laptops on your desk, is acting as a layer 3 router.
Yep.
Now, I have to pause here. Why make the access layer layer 3? Historically, we always used simple layer 2 switching for the endpoints. It was just cheaper and easier.
Because layer 2 switching relies on spanning tree protocol, which is, well, it's the bane of network engineers everywhere.
Oh, I've heard the horror stories.
Yeah, if you plug two layer 2 switches into each other with redundant cables to prevent outages, spanning tree intentionally blocks one of those cables to prevent an infinite broadcast loop.
So you're buying expensive fiber optic cables and just turning half of them off.
Exactly. You end up wasting half your bandwidth. And worse, when a link fails, it can take precious seconds for the network to recalculate and unblock the backup path.
Which causes dropped calls, application timeouts, frustrated users.
Right. So by making every switch a layer 3 router, we run a routing protocol called ISIS everywhere. Yeah. Routing protocols don't block redundant links, they load balance across them. So we completely eliminate spanning tree protocol.
Just gone.
Gone. We also eliminate the need for legacy gateway redundancy protocols like HSRP. The physical network just becomes an incredibly fast, highly redundant, dumb highway system. Its only job is to provide pure IP connectivity from any node to any other node.
Okay, but if the physical network is just a dumb highway for the switches to talk to each other, where does the actual user traffic live? Like my laptop sending an email.
That lives in the overlay.
Okay.
The overlay is a logical virtual network built entirely on top of that physical highway, and it achieves this using a technology called VXLAN encapsulation.
Encapsulation, so wrapping the data. When my laptop sends a standard Ethernet frame into the network, the first switch it hits, which I think is called the Fabric Edge node, takes my entire original frame and just shoves it inside a brand new VXLAN tunnel header.
Yep, it wraps it up.
And then it shoots that encapsulated package across the underlay highway to the destination switch, which unwraps it and hands the original frame to the server.
That is the exact mechanism, yes. But, and there's always a but, it raises a critical problem.
What's that?
How does your local switch know which destination switch across the entire campus has the server connected to it?
Oh, right. Because in a traditional network, if a switch didn't know where a mask address lived, it would just broadcast a shout to every single device on the network asking, who has this address?
Right, an ARP request. And doing that across a massive enterprise with 50,000 devices.
That would absolutely melt the network. Broadcast storm.
Exactly. So how does SDA solve this discovery problem without broadcasting? It uses a control plane protocol called LISP, Locatory Deseparation Protocol.
LISP. Okay, let's find an analogy here because the acronyms in the source material get really dense. It feels a bit like a modern postal forwarding system, maybe.
That's actually a great way to look at it. Instead of shouting to every neighborhood, SDA uses a centralized LISP map server, which acts like the central post office database.
Okay.
Endpoints, like your laptop or your phone, are called EIDs, endpoint identifiers. The physical switches they connect to are called RLOC's routing locator.
Okay, EIDs are the devices, RLOCs are the locations. So when my laptop connects to the network in Building A, the switch in Building A immediately sends a silent message to the central LISP map server saying, hey, I have this specific EID located at my RLOC.
Exactly, it registers it.
And later, when a server in Building B wants to send me a video stream, its local switch doesn't broadcast. It just queries the map server. Hey, where's this laptop? And the map server replies, send it to the switch in Building A. Boom. A direct, efficient VXLAN tunnel is formed.
Total efficiency. No broadcast storms taking down the network at 2 a.m.
That is so slick. But here's where it gets really interesting, though. Because reading through these architectural guides, SDA solves one of the absolute worst nightmares in the history of network engineering.
Oh, I know what you're going to say. IP access control lists. ACL.
The ACL nightmare.
Yeah.
Every engineer has scars from this.
It's so true. In a traditional network, if you want to block, say, the guest Wi-Fi subnet from reaching the HR servers, you write an access list based on IP addresses.
Right.
And over the years, as projects come and go, engineers add lines and lines to these lists. Eventually, you have core routers burdened with thousands of lines of security rules.
And the terror is that clearing a router and you see line 402, which says permit IP 10.1.5 to 10.U.9.0, and you're terrified to delete it because it might break some legacy database application running in the basement, but it might also be totally useless residue from 5 years ago.
It just becomes a bloated, overlapping mess. Nobody wants to touch it.
So how does SDA fix this?
SDA completely obliterates the IP address problem by introducing scalable groups. This is the ultimate realization of intent-based networking, or IBN.
Intent-based networking.
Yeah. Instead of writing rules based on shifting IP subnets, you log into the central DNA center controller and you define security policies based purely on user identity. You create a scalable group tag, or an SGT.
Okay.
So you have one tag for employee, one for HVAC systems, one for guest.
And then you just look at a simple visual grid in the software, right? Can a guest talk to an employee? Deny. Can the HVAC system talk to the internet? Deny. You just declare your business intent. You literally don't type a single IP address.
Not one. You declare the intent, and the controller translates that into reality. When a user logs onto the network and authenticates, they are dynamically assigned their SGT.
Their tag.
Right. And that tag is actually embedded directly into that flexible VXLAN tunnel header we talked about earlier.
Oh, wow.
Yeah, so as your data flies across the fabric, the final destination switch looks at the SGT inside the header and either drops or permits the packet based on your intent grid.
It is brilliant. It really is. But I am going to play devil's advocate here for a second.
Go for it.
SDA and DNA Center are incredible if you are building a brand new multi-million-dollar campus or if you're an exclusive Cisco shop. But what if you are managing an enterprise with a vast mix of legacy devices, different vendors, cloud servers, and you just need a way to stop humans from making manual errors?
Then you are dealing with the insidious problem of configuration drift.
Configuration drift.
And to solve that, the sources point us toward configuration management tools like Ansible, Puppet, and Chef.
Okay, let's talk about configuration drift. Because the reading provides this painfully relatable scenario. Imagine you have two network engineers, Alice and Bob.
Poor Alice and Bob, always getting into trouble.
Always. So at 1:00 a.m., a critical branch router goes down. We'll call it BR22. Bob logs in, types a few imperative commands, fixes the routing issue, and, totally exhausted, goes back to sleep. Then, at 4 a.m., Alice gets an alert about a different router, BR33. She logs in, applies a slightly different emergency fix, and goes to sleep.
So they both solved the immediate outage, but neither of them perfectly documented the exact syntax they changed. So a few months later, BR22 and BR33 have underlying configurations that are slightly different from the other 98 branch routers in the company. The network has subtly drifted from its intended ideal baseline.
And when you scale that up over years, this drift creates an incredibly fragile network where troubleshooting becomes impossible because every single device has become a unique snowflake.
Exactly. Snowflake configs are the enemy. The foundational fix here is a change in human behavior. You have to stop logging directly into the routers.
Just ban it entirely.
Yes. Instead, you keep centralized configuration files on a secure server. You treat these files as the absolute single source of truth, and you manage them using version control systems like Git.
Which is exactly what software developers do with their code. With a tool like Git, you can see exactly who changed a file, at what exact millisecond, and highlight the exact characters they added or deleted.
Yeah.
There are no more mystery changes.
None. It's fully audited.
Okay, let's unpack this further because I can hear the skeptics. They're thinking, is it really worth learning complex automation tools, setting up Git repositories, writing automation scripts, just to change a simple IP address on a router? Like, why not just SSH into the box and type the command in 5 seconds?
Well, if we connect this to the bigger picture, it is never just one IP address.
Fair point.
What happens when the cybersecurity team dictates, hey, we found a vulnerability and we need to update the SNMP monitoring strings and the syslog server destinations on all 500 of our branch routers by tomorrow morning?
Oh, wow. Yeah. Executing that manually takes hours of tedious typing.
Huh.
And human fatigue guarantees you'll make a typo on at least a few of them, which just creates new security holes.
Exactly. The manual method simply doesn't scale.
So how do these tools actually deploy the fix at scale?
This brings us to the profound shift from imperative execution to declarative execution.
Imperative versus declarative. Okay, break that down.
When you type commands manually, you are being imperative. You are providing the step-by-step instructions on how to change the state. Enter config mode, select the interface, type the IP exit.
Right.
Automation tools generally prefer a declarative approach. You simply define the end state you want, just make sure the syslog server is set to this IP, and the software figures out the necessary steps to make that reality happen.
And the most popular tool for this in the networking world seems to be Ansible.
By far. Ansible's massive advantage is that it is agentless. You don't need to install any proprietary software onto the Cisco router itself.
Oh, that's huge.
Yeah, Ansible simply uses the router's existing SSH or NetConnect protocols to log in and push the changes. You define your logical workflows in files called playbooks.
Playbooks. And the sources mentioned, Ansible uses configuration templates and variables to solve that 500 router problem. So you don't store 500 massive, identical text files.
No, that would be a mess.
Instead, you create one single, flawless template for a branch router using a templating language called Jinja 2.
Jinja 2, yes.
And Jinja 2 acts like a stencil. Where the unique IP address goes, you just cut out a hole and put a variable placeholder.
Perfect analogy. And then you maintain a separate variables file, usually written in YAML format, which acts as your paint palette. It just cleanly lists the specific IP addresses, host names, and routing numbers for each of the 500 locations.
So it's just a clean data list.
Right. When you run the Ansible playbook, it merges the YAML variables into the Jinja 2 stencil, and it dynamically pushes a flawless, standardized configuration to all 500 routers simultaneously. Snowflake configurations are eliminated forever.
That is incredibly powerful. Now, the sources do contrast Ansible with two other heavyweights, Puppet and Chef. How do they differ?
The biggest architectural difference is push versus pull. Ansible uses a push model. You run the script on your centralized server, and it actively pushes the changes out to the network. Puppet and Chef generally use a pull model.
So with Puppet, the end devices are actively checking in.
Exactly. Puppet relies heavily on that declarative language we mentioned, stored in files called manifests. But to make it work, it typically requires an agent like a small piece of Puppet software running locally on the device itself. That agent continuously pulls the manifest from the main server, checks its own local configuration, and if there is a discrepancy, the agent corrects it automatically.
And Chef operates similarly, right, using all those culinary terms.
Yeah.
The logic is stored in recipes, and related recipes are grouped into cookbooks.
Yep.
But from what I'm reading, because both Puppet and Chef traditionally require you to install an agent on the device, and many legacy network switches just don't support third-party software installations, Ansible's agentless push model basically won the networking war.
Precisely. Chef and Puppet are phenomenal for managing massive fleets of Linux or Windows servers, but for pure network infrastructure, Ansible's ability to just SSH into a dumb switch makes it the undisputed king.
Makes total sense. Wow, we have covered a massive amount of architectural ground today.
We really have.
We started by extracting the brain from the traditional hardware switch and migrating it into a centralized controller. We learned how RESTful APIs and lightweight JSON payloads allow software to communicate statelessly with that brain. We explored how Cisco SDA uses a routed underlay and VXLAN overlays to build a unified fabric, using LISP to eliminate broadcast storms and intent-based networking to kill the IP ACL nightmare.
Goodbye, ACLs.
Seriously. And finally, we looked at how tools like Ansible use templating and version control to prevent massive configurations from drifting into fragile chaos.
It's a whole new world.
It is. So what does this all mean for you? Well, Whether you are an aspiring network engineer studying for your next certification or just a professional who relies on cloud applications and video calls to do your job, this automation is the invisible glue.
Yep.
It's the only thing keeping the modern digital world from collapsing under its own massive weight. Understanding this shift from manual imperative CLI typing to software-defined declarative intent is the ultimate shortcut to understanding how modern IT infrastructure actually scales.
It truly is the foundation of the modern cloud. And, connecting everything we've discussed today raises a fascinating, perhaps provocative, final question.
Oh, I like those. What is it?
Well, if networks are now entirely software-defined, if they're configured by Git code repositories built with Jinja 2 templates and managed by stateless REST API calls, will the network engineer of the future even need to understand how a physical fiber optic cable or a hardware ASIC chip actually works?
Oh, wow.
Right? Or are we rapidly approaching a reality where network engineers are simply software developers who happen to specialize in moving data? Something to monitor.
That is a great question to leave off on. Are we all just becoming coders? Either way, one thing is for certain. You never have to drive out to that intersection in the rain to manually program the traffic lights ever again. You can do it all from the command center. Thanks for taking this deep dive with us.